Hi Chem 1 students, this is just a recap of discussion 1-1. So it has all the stuff we talked about with atomic structure, but also the average atomic mass piece as well. So if you ever miss class and just want a quick recap, or if you want to hear the information again, you can access these videos. I also have a couple just short videos just to show you little skills that 3 to 4 minute videos to show you how to calculate neutrons or how to calculate average atomic mass. So you can use those as well. Okay, so let's talk about atomic structure. Now, imagining we had a chunk of copper. If we cut it in half, we would have 2 chunks of copper, right? If we kept chopping it up further and further and further, would we get to a point where we couldn't chop it up anymore? Yeah, absolutely. Eventually, assuming we had some very, very high-tech fancy equipment, we would get to the smallest possible unit of a thing that we could still call copper, and this would be an atom of copper. Okay? That's the smallest piece of an element that still retains the properties of that element. So subatomic particles are particles that exist within an atom. Okay? So the atom is the smallest thing that has the properties of that substance, but there certainly are smaller things within the atom. Protons, neutrons, and electrons. And you probably learned about those in 8th grade, and so hopefully you remember a little bit of that. All right, now when we talk about the subatomic particles, we need to know where they're located and their charge and their mass. So protons are located in the nucleus, and they have a positive 1 charge. Okay? You can remember that because protons are positive. They both start with P. And they have a mass of 1 atomic mass unit. Neutrons are also located in the nucleus, and neutrons are neutral, okay? And they have a mass of 1 atomic mass unit as well. Now, electrons have some differences. They're located in the electron cloud outside the nucleus, and they have a charge of -1. Now, electrons do have mass, but it's so small that we say that it is negligible. This just means that it's near 0. I always tell people to imagine that you stepped on a scale and you looked at your weight and then you caught a fly. Would your weight change? No, because the fly's mass is negligible compared to yours. It has mass, it's just very small. So compared to the proton and the neutron, the mass of the electron really barely registers. Okay, so atomic number, where can I find it? On the periodic table. I suggest you use the one on Google Classroom. It has everything you need and nothing that you don't. So the number of protons in the nucleus determines an atom's atomic number. So for example, all hydrogen atoms and only hydrogen atoms have an atomic number of 1, which means that they have 1 proton in their nucleus. All right, so how many protons are present in an atom of nitrogen? So take a look at your periodic table, and I'm actually going to show you my periodic table so you can see it. Here's my periodic table. When I look at nitrogen, first of all, one thing I love about this periodic table is this key here at the top, okay? If you ever forget which number on the periodic table is the atomic number, just look up here, okay? So the atomic number in this periodic table is located right below the symbol. So for nitrogen, if we want to know its atomic number or number of protons, we look right here, and we see that the answer is 7, okay? So that's how many protons are present in an atom of nitrogen and its atomic number. Those are the same thing. Now let's talk about electrons. First, we have to think about their charge. What charge do electrons have? Well, they're negative. So in a neutral atom, how do the number of protons relate to the number of electrons? They're going to be equal. Okay, so now we have 3 things that are equal in a neutral atom: protons, electrons, and atomic number. Now, the number of electrons can change. We're going to discuss that later. That's something called an ion, and you might have learned about that in 8th grade as well. But in this topic, we're just going to talk about neutral atoms. So for now, we know that the protons are equal to the atomic number, and for the time being, the electrons are the same as well, since we're talking about neutral atoms. All right, so the relationship between protons, electrons, and atomic number, how would you fill in those blanks? The atomic number equals the number of protons, and it also equals the number of electrons, but again, only in a neutral atom. Now, neutrons are a little bit more complicated because for any given element, we have multiple isotopes. So an isotope is an atom with the same number of protons, but a different number of neutrons. So the number of neutrons in an atom can change, and when it does, it forms a different isotope of an atom. Now, how are we going to figure these out if they can change all the time? We're going to use something called mass number. So let's think back to a couple minutes ago when we talked about which ones have significant mass of the subatomic particles. We said that protons and neutrons had significant mass, right? They each had a mass of 1 atomic mass unit, and electrons were negligible in comparison. So for any given isotope, we can calculate something called the mass number. And this is the number of protons plus the number of neutrons. So here's a question to think about. What is the mass number of an isotope of fluorine with 10 neutrons? Okay, so here's what we're going to have to do to solve this. First, we're going to have to think about what the mass number is, first of all. So the mass number is, let me move this. The mass number is the number of protons plus the number of neutrons. And what we're trying to find here is the mass number of an isotope of fluorine with 10 neutrons. Okay, so in order to calculate this, we need the protons and the neutrons. The problem says there's 10 neutrons, so that's great. But where are we going to get the protons? So this is where we're going to have to go back to our periodic table. So we're talking about fluorine. So let's refresh. Where do we get the number of protons in fluorine? We have to use the atomic number. So for fluorine, that atomic number is 9. So that gives us the number of protons. So to calculate the mass number of this isotope, we take the protons plus the neutrons, and we get 19. Okay. So let's look at an example of two isotopes, chlorine 35 and chlorine 37. 35 and 37 are the mass numbers of these isotopes. So this is one way we can express the mass number. So let's think about what they would have in common. They're both going to have 17 protons. Why? Well, because they're both chlorine, and the atomic number of chlorine is 17. They're also going to have the same number of electrons, and that's because these are neutral atoms. So protons and electrons will be the same. Now, what's going to be different about these? Well, we know the mass number is different, right? Because these are the mass numbers and they're not the same. So what else has to be different? If the mass number is the sum of the protons and the neutrons, and the protons are the same, then we know that the neutrons must also be different. Okay, and that's the definition of an isotope, right? They have different numbers of neutrons. Now, there's another way that we can express the mass number of an isotope. Okay, we can write it like we've been doing. We have copper 65, okay, here, or we can write the symbol, and we can put the mass number in the upper left-hand corner and the atomic number in the lower left-hand corner. Now, technically, I don't even need to write that atomic number for you because you could look on the periodic table and get it quite easily. But sometimes we include it, and that's where we put it when we do. So I want you to pause this for a moment and ask yourself how many protons, neutrons, and electrons are found in this neutral isotope of copper. So pause for a second, and then when you're ready to check your answer, press play again, and I'll go over it. Okay? All right, so this is our isotope. It's copper 65. So again, another way to write that would be copper 65. Now, this is the atomic number. We want the protons, the neutrons, and the electrons. So hopefully we remember that the atomic number is always equal to the number of protons. So it's 29. Since this is neutral, that's also the number of electrons. Now, remember that the mass number is the number of protons plus the number of neutrons. Now this right here is our mass number. Okay, so 65 is equal to the sum of the protons and the neutrons. We know that we have 29 protons. We can subtract 29 from both sides, and we get that there are 36 neutrons. Okay? The most common mistake I see people making with this is that they forget what this number is. Okay? So try to remember for yourself that this is the mass number and not the number of neutrons. This is the sum of the protons and the neutrons, and that will help you out a lot. All right. So let's talk about these two isotopes. Now in class we dragged dots to the different things to say whether they were the same or different. But if we have carbon 12 and carbon 14, again, these are the same element. So they must have the same number of protons. They're both neutral, so they also have the same number of electrons, but they have different mass numbers here, 12 and 14. So the mass number will be different. And the thing that makes the mass number different is that they have different numbers of neutrons. Okay, so here's what I would like you to do just for a moment. I'd like you to pause, copy down this table, and try to fill it out. I know the last line's a little hard to see. That's 55 and 25 for the mass number and the number of protons. And then when you're done looking at this, press play and we'll go over it. So you will need a periodic table to do this. Okay, let's take a look at the first one. Now we know that the element is boron, and it has a mass number of 11. It seems like that might not be enough information to fill out the rest of it, but we're going to find out that it is. Okay, so if we look at the periodic table, we would see that the atomic number of boron is 5. And we know that atomic number is always equal to the number of protons. Since this is a neutral atom, that's also equal to the number of electrons. So for this exercise, the three columns, atomic number, protons, and electrons, are going to be the same. So the only thing we really have to figure out then is the number of neutrons. Since the mass number is 11, and we know the protons plus the neutrons equals the mass, we must have 6 neutrons. Okay, now the next one, I didn't even give you the element. So how are we going to figure that out? We know that the number of protons is equal to the atomic number, and that identifies an element. So this element is fluorine, because fluorine has an atomic number of 9. Now, we weren't given the mass number here, but we were given the number of neutrons. So we can add the protons and neutrons to get the mass number. For the next one, bromine, we know the atomic number is 35, so that gives us protons and electrons. And then to get the mass, we would add the protons and the neutrons, and we would get 80. The very last one, to figure out the element, we have to use the number of protons, which is 25. So we would see that it is manganese. It has an atomic number of 25 and a mass number of 55. If you're having trouble with this, please reach out so I can help you with this. It's something that sometimes requires a little bit of practice, but it gets a lot easier the more you try it. Okay. So let's talk about average atomic mass now. Now you might have noticed that so far we've been talking about mass number, okay? And we've been talking about whole numbers, right? 1965. But if you look on the periodic table, and it's a little hard to see here, let me see if I can zoom a little more for you. If we look at the periodic table, there we go, better. You might notice that most of these masses are in the upper left-hand corner. This is the atomic mass, and these aren't whole numbers, which is funny because so far we've just talked about mass number as a whole number. So where is this number on the periodic table coming from? Well, this number on the periodic table takes into account all the different isotopes for an element, okay? So the average atomic mass that's on the periodic table is a weighted average of isotopes based on their natural abundance, so how much they occur naturally in nature. Now, using the periodic table, what's the average atomic mass of neon? Okay, so again, we would look at our periodic table and say, all right, here's neon, I know the mass is up here in the upper left, and the average atomic mass of neon is 20.179. Now, what we're going to do, is we're going to talk about why we need to calculate this. So I want you to imagine that there's a room with 100 people in it. 99 of those people weigh 170 pounds, and one person weighs 100 pounds. Would it be reasonable to say that their average weight is 135? No, right? Most of those people weigh 170 pounds. So their average weight is probably pretty close to 170, right? It's not right in the middle of those two. So the same thing is, we're going to see the same thing with isotopes. Remember we talked about how chlorine had two isotopes, 35 and 37. The periodic table doesn't say that the average is 36. It says 35.45. And that's because chlorine 35 is more abundant. So it pulls the average closer to itself. So I want to show you how to calculate average atomic mass. Okay? Now, the first thing that we're going to do is we're going to change the percent abundance to a decimal. And then we're going to multiply that decimal by the mass number of the isotope. Okay? So I'm going to actually do this on the document camera because I think it's a little easier to see. All right, so we have two isotopes. We have chlorine 35 and chlorine 37. So the masses here are 35 and 37. And the abundance is approximately, this is rough, 75% and 25%. Okay? Zoom out a little, that's a bit too much. There we go. Okay, so we have to change that percent to a decimal. So the decimal place is here, and the easiest way to do that is to move it 2 places to the left. Okay? 2 places to the left. So I get 0.75 and 0.25. Now, I have to multiply the mass times the percent as a decimal. Okay? So I have 35 times 0.75, and I have 37 times 0.25. And I get 26.25 and 9.25. Okay? I have to add those results together, and when I do that, I get 35.5 atomic mass units. That's pretty close to what's on the periodic table. It's not exact because we used kind of rough percentages, but it's very close. A couple things to notice about this. First of all, it has to still be in between those two numbers, right? It's a weighted average, but it's still a type of average. Secondly, it should be closest to the most abundant isotope. Now, I'm going to give you a caution. Never, ever, ever do not divide by 2, okay? We don't have to do that when we do a weighted average because we're taking that into account with the percentage abundances, okay? That's probably the most common mistake people are going to make here. Okay, so what I would like you to do now is I would like you to try this practice problem, okay? I want you to calculate this element's average atomic mass and identify the element on your periodic table, okay? I want you to pause, and when you're ready to go over it, press play, and I will go over it with you, okay? Okay, so let's take a look at the document camera, and we'll go over this. All right, so I have my mass of my isotope and the abundance. Now, first, I have to change the percentage to a decimal, okay? So I get 0.198, and I get 0.802. Next, I multiply the mass by its percent abundance as a decimal. And when I calculate that, I get 10.81. Now, let's make sure that this makes sense. Is it between those two numbers? Yes. Is it closer to the more abundant isotope? Yes, it's closer to 11 than it is to 10. Okay? Now, if we look at our periodic table, we're looking for something that has a mass of about 10.81, and look, we found it. It's boron. Okay? So this is boron. All right. Do the practice. Let me know what questions you might have, and reach out if you need any help. I would love to work with you on this. All right. Have a great day.